Now we'll look at our first implementation of an algorithm for solving the dynamic connectivity problem called quick find. This is a so-called eager algorithm for solving connectivity problem. The data structure that we're going to use to support the algorithm is simply an integer array indexed by object. The interpretation is that two objects, P and Q, are connected if and only if their entries in the array are the same. So, for example, in this example with our 10 objects, the ID array that describes the situation after 7 connections is illustrated in the middle of the slide, so that at this point 0, 5, and 6 are all in the same connected component because they have the same array entry 0. 1, 2, and 7 all have entry 1, and 3, 4, 8, and 9 all have entry 8. So that representation shows that they're connected. And clearly that's going to support a quick implementation of the find operation. We just check the array entries to see if they're equal. Check if P and Q have the same ID. So 6 and 1 have different IDs. 1 has ID 1, 6 has ID 0. They're not in the same connected component. Union is more difficult. In order to merge the components containing two given objects, we have to change all the entries whose ID is equal to one of them to the other one. And arbitrarily, we choose to change the ones that are the same as P to the ones that are the same as Q. So if we're going to union 6 and 1, then we have to change entries 0, 5, and 6, everybody in the same connected component as 6, from 0 to 1. And this is, as we'll see, this is a bit of a problem when we have a huge number of objects because there's a lot of values that can change. But still, it's easy to implement, so that'll be our starting point. So we'll start with a demo of how this works. So initially, we set up the ID array with each entry equal to its index. And so all that says is that all the objects are independent, they're in their own connected component. Now when we get a union operation, so say 4 is supposed to be union with 3, then we're going to change all entries whose ID is equal to the first ID to the second one. So in this case, we'll change the connect 3 and 4 means that we need to change the 4 to a 3. And we'll continue to do a few more so you'll get an idea of how it works. So 3 and 8 now. So to connect 3 and 8, now 3 and 4 have to be connected to 8, so both of those entries have to change to 8. Okay, so now what about 6 and 5? So again, we change the first one to match the second one. So to connect 6 and 5, we change the 6 to a 5. What about 9 and 4? So now we have to change to connect 9 and 4, we have to change 9's entry to be the same as 4's. So now we have 3, 4, 8, and 9 all have entries 8. They're all in the same connected component. 2 and 1 means that we connect 2 and 1 by changing the 2 to a 1. 8 and 9 are already connected. They have the same entries in the ID array, so that connected query, that find, says true, they're already connected. And 5 and 0 have different entries. They're not connected, so we'd return false in that case, not connected. And then if we want to connect 5 and 0, then as usual, we'll connect the entry corresponding to both 5 and 6 to 0. 7 and 2, union 7 and 2, that's an easy one. And union 6 and 1, so now there's 3 entries that have to get changed. All those zeros have to get changed to 1s. That's a quick demo of quick find. Now next we'll look at the code for implementing that. Okay, with this concrete demo in mind, then moving to coding up this algorithm is pretty straightforward. Although it's an interesting programming exercise that a lot of us would get wrong the first time. So let's start with the constructor. Well, we have a private integer array, that's our ID array, that's the data structure that's going to support this implementation. The constructor has to create the array and then go through and set the value corresponding to each index I to I. That's straightforward. The find operation or connected operation, that's the easy one. This is the quick find algorithm. So it simply takes its two arguments, P and Q, and checks whether their ID entries are equal and returns that value. If they're equal, it returns true. If they're not equal, it returns false. The more complicated operation to implement is union. And there we find first the ID corresponding with the first argument, and then the ID corresponding to the second argument. And then we go through the whole array and looking for the entries whose IDs are equal to the ID of the first argument and set those to the ID of the second argument. That's a pretty straightforward implementation. And I mentioned that a lot of us would get us wrong. The mistake we might make is to put ID of P here rather than first picking out that value. And you can think about the implications of that. That's an insidious bug. So that's a fine implementation of quick find. Now the next thing is to decide how effective or efficient that algorithm is going to be. And we'll talk in some detail about how to do that, but for this it's sufficient to just think about the number of times the code has to access the array. As we saw when doing the implementation, both the initialize and the union operations involved a for loop that go through the entire array. So they have to touch, in a constant proportional to n times, they have to touch an array entry. Find operation is quick, it just has to, a constant number of times, check array entries. This is problematic because the union operation is too expensive. In particular, if you just have n union commands on n objects, which is not unreasonable, they're either connected or not, then that'll take quadratic time, n squared time. And one of the themes that we'll go through over and over in this course is that quadratic time is much too slow, and we can't accept quadratic time algorithms for large problems. The reason is they don't scale. As computers get faster and bigger, quadratic algorithms actually get slower. And let's just talk roughly about what I mean by that. A very rough standard, say for now, is that people have computers that can run billions of operations per second, and they have billions of entries in main memory. So that means that you could touch everything in the main memory in about a second. It's kind of an amazing fact that this rough standard is really held for 50 or 60 years. The computers get bigger, but they get faster. So to touch everything in the memory is going to take a few seconds. And that was true when computers only had a few thousand words of memory, and it's true now that they have billions or more. So let's accept that as what computers are like. Now, but that means is that with that huge memory, we can address huge problems. So we could have billions of objects and hope to do billions of union commands on them. But the problem with that quick find algorithm is that that would take 10 to the 18th operations, or say array accesses or touching memory. And if you do the math, that works out to 30-some years of computer time. Obviously not practical to address such a problem on today's computer. And the reason is, and the problem is, that quadratic algorithms don't scale with technology. You might have a new computer that's 10 times as fast, but you can address a problem that's 10 times as big. And with a quadratic algorithm, when you do that, it's going to be 10 times as slow. That's the kind of situation we're going to try to avoid by developing more efficient algorithms for solving problems like this.